talk about three specific methods today. They allow us to measure specific optical effects from a given data set without requiring access to the microscope. And then considering these effects during refinement produces better reconstructions. So all of this I've done at the LMB with Schreres and Takanori. So all of this will be available to the public very soon with the next release of Relion 3.1, possibly next month already. So the specific effects that I will talk about are two types of higher order aberrations, symmetrical and antisymmetrical ones, and anisotropic magnification. So let's begin with the aberrations. So in order to explain this, I'll have to go through some very simplified optics. So in a TEM, when an electron passes through our very thin sample, most of the electron does not scatter, it just passes right through. One small fraction of it scatters and essentially performs a Fourier transform of the image that it sees. So that for every 2D spatial frequency k in the image, there is a corresponding ray moving that direction with that amplitude and phase. There are no discrete rays, of course, unless we look at crystals. It's a continuum of rays. And further below, there are lenses, or one lens, that serves to refocus the scattered rays. And now if we had a perfect lens, which we don't, and if we used it to take an image in focus, then all those scattered rays would arrive in phase. That is, the ones traveling through the middle would be slowed down by the lens just enough so that the ones from on the outside can catch up, just like on a glass lens. However, although even all those scattered rays would be in phase with each other, they would still exhibit a small phase shift versus the unscattered ray. And that would give us a small amount of contrast, and that's what material scientists would work with. In Cryo-EM, we of course like to take images out of focus. And then if the scattered rays are in phase down here, then they can no longer be in phase up there. So because they all have different phases compared to each other, their phase shift, their phase delay versus the unscattered ray varies. And this is what gives rise to our CTF. However, in the peaks and the troughs of the CTF, we obtain about 15 times higher contrast this way. Right, and this phase delay phi is what I will refer to as the aberration or phase delay. Now, another very important property is Friedel symmetry. So because the image that the electron sees is real valued, or we model it that way, its Fourier representation exhibits this symmetry. That is, the complex amplitudes at spatial frequency k is the complex conjugate of that at minus k. So the absolute amplitude is symmetrical, the phase is anti-symmetrical. Now, if the scattered rays corresponding to k and minus k are delayed by different amounts, this breaks Friedel symmetry. Now, this does not make us see imaginary numbers, unfortunately, because the image arises from the interference between the scattered and the unscattered rays. But what it does is it shifts the phases of the respective image waves for frequencies k. And the most common situation we will see this is under a tilted beam, but it's not the only situation. So here an example. To the left, you see a simulated example of a beta gel. On the left, you see the undistorted image, and on the right, you see how the very high frequencies are shifted very much to the right, while the lower frequencies remain unimpaired. Right. So what we can always do is we can split the phase delay up into a symmetrical component, which is just the average of the two sides, and an anti-symmetrical component. And now the symmetrical component produces the CTF, and the anti-symmetrical one introduces a new phase shift. Now, this is just owing to tradition. I mean, at some point, we have defined the CTF to be a real valued function, so the phase shift has to be treated separately. We could also think of the phase shift as the phase angle of the CTF, but we don't. However, because the effects are different, we have to estimate these two separately and treat them separately. So until now, in Relion 3.0 at least, for the CTF, we used only these three effects, basis functions. So we have a constant phase shift or amplitude contrast term, a quadratic astigmatic defocused term with 3 degrees of freedom, and a radial asymmetrical fourth order term for the spherical aberration. These are the only 5 degrees of freedom for this traditional CTF. And on the antisymmetrical side, we've introduced beam tilt for Reliant 3.1, 3.0. In Reliant 3.1, we will allow for arbitrary Zernike polynomials in both columns. Now, more importantly than the fancy new model, these are the polynomials, by the way. There's nothing very special to them. We don't use their orthogonality, but so they come in even and odd bands, which are either anti-symmetrical or symmetrical. The frequency increases, as does their number, and they come in pairs. So by constructing linear combinations of corresponding functions, we can rotate them into any angle. These are the ones that we have considered so far. These two are just describe the shift of the particle, and the true position of the particle is unknowable, so we don't really care about these. Right. Now, more important than the model, of course, is that we now have methods to estimate the coefficients corresponding to these Zernike polynomials. All of these methods, or both of these methods, require only one scan through the data, which takes on the order of 1 hour, usually less. And then the Zernike polynomials are fitted and can be used in the next refinements. Because these are refinement methods, we require a previous 3D map that has been obtained without knowing these effects, and all the angles and the foci and everything that allows us to make a prediction that corresponds to every observed particle image X. So here an example, to scale, by the way, just to remind you. So this is the signal that we predict, and that's supposed to be hidden in this polished image here. So you see the two dark dots, if you look carefully. Maybe don't. And remember the letters, by the way. I will always refer to the prediction as V and to the experimental image as X. So to come clean here, the anti-symmetrical aberrations are essentially the same as the beam tilt estimation in Reliant 3.0, just with a different model. But it's the simplest of the three methods that we'll be talking about today, so I'll use this as an entry point. So for the anti-symmetrical aberrations, we would like to represent a angle field, one angle for each Fourier pixel k, as a linear combination of anti-symmetrical Zernike polynomials. And these are the unknowns, these red letters. And then these phase angles produce phase shifts. That's just numbers on the unit circle in the complex plane that, when multiplied to the predicted images, rotate them as closely as possible in least square sense to the complex amplitudes of the in the observed images. And this is to be minimized over all particles and all frequencies. Now, the problem with this is that it's, of course, for one nonlinear, and for the other, we would like to always have millions of particles if possible, with hundreds of thousands of pixels each. So doing this nonlinearly, iteratively would be prohibitive, especially because the particles are all stored on disk and would have to be loaded over and over again. Instead, we can do something much more elegant. We can reorder the terms, and when we put all of the terms corresponding to one given frequency k together, we see that the R is the same for all of them. And it's a sum of quadratic functions, which we can reduce to one single such quadratic function, which is defined by its vertex, its minimum q, and its weight or curvature w. Also an absolute offset, but this is ignored here because we only look for the minimum. And now when we minimize this over all the frequencies, this can be done trivially in fractions of a second, nonlinearly. It produces the same minimum as this here. It's not an approximation. And these numbers here, the blue ones, these we can estimate or compute by just scanning through the data once. We load each particle from disk and make the corresponding prediction. For the weights, we just add up the squared amplitudes, and for the Q, the correlations. And then we have it. But more important than making the problem tractable this way is we can also inspect the per pixel optimal phase shifts. So these Q are, again, numbers in the complex plane, somewhere close to the unit circle. And when we look at their phase angles, we usually see the signature of a beam tilt. That is a positive phase shift on one end and a negative one on the other, and a cubic growth in between. But in some cases, we actually see more interesting things. like these trefoil aberrations. This is the most extreme case, and we'll be looking at that a little more. Or another trefoil, and this thing that might be a secondary coma, but it's a little hard to tell. And with our new Jasenko model, we can now express this quite well. So in this case, it's specifically these trefoil terms. These are the beam tilt terms in the third order. And now, when we consider these, we can also fit something that looks like this, which becomes positive 3 times and negative 3 times. Right, so the antisymmetrical aberrations were already known. For the symmetrical ones, this is new territory. I've done something similar, but here we try to find, first off, until now, we have used this CTF, which is just a negative sign of some phase delay gamma, which consists of these 3 terms, a constant, a quadratic, and a 4th order one. Note there are no linear or 3rd order terms because it has to be symmetrical. And now, right here on the diagram, see the phase shift, 1 term, and 3 defocus terms, and again, 1 spherical aberration term. So now, it makes sense to estimate these low order terms per particle or per micrograph in some situations, very often. So we don't want to touch the old CTF. We only want to add 1 offset, which is global or partly global, constant for 1 big chunk of the data set. And this is based on the expectation that the higher order aberrations change more slowly than the lower order aberrations. That is something that microscopy people seem to think. I have no experience with it. But now we look for a constant such offset while this here varies. Right, and here again, we want to minimize a square loss. Now the CTF is unknown, and it's very much nonlinear because this thing is in the sign here. I mean, this is the phase delay delta, which is a linear combination of now symmetrical Jasenko polynomials. And yeah, we want to find the optimal such coefficients D, which gets the V's as close to the X as possible, X's as possible.
Sorry, what does that say, no CTF?
Well, there's no CTF in the V. The prediction is made without us modulating it with the CTF, because we are looking for the correct CTF to multiply to this. Okay. That's all. The X already contains the CTF, of course, because... Right, and what we can do now is just apply a basic trigonometric identity and transform the sum inside the sign into a linear combination of the sines and cosines. But note that the lower order terms are known here. So it's, but just redefining the sine and the cosine over unknown delta as our new unknown, our new per pixel unknown t, we can transform a nonlinear one-dimensional problem per pixel into a linear two-dimensional problem. And we can go back and forth between the t and the delta, of course. Right, so now our CTF is something linear. We can plug it in here and put all of these coefficients on one side. We see this is, oops, this is really a linear problem for a given k. And more specifically, we can, it's again a sum of parabolas, but now in 2 dimensions, 2 real dimensions instead of 1 complex dimension. But it is an actual difference because the weights become anisotropic. So again, we reorder the terms, we put everything together that belongs to a given k, so that the t is the same, the phase shift for a given frequency pixel k, the shift in the CTF has to be the same for the entire data set, no matter what the actual phase of the CTF is for a given particle. And now, when we group these together, we can again transform them into one single quadratic expression, where the weight is now a symmetrical 2x2 matrix, so it's anisotropic. And the TKs, in order to obtain those, we don't divide by the weights, but instead we invert this symmetrical 2x2 matrix. But it's essentially the same, just in 2 dimensions. And like before, we just need to iterate through the data set once. It can be the same iteration as the previous one. And we just sum up what these W's and B's for each k. that is the weights and well, the things that will then produce the optimal phase shifts for each pixel. And once we have that, we can optimize this non-linearly again within fractions of a second. Right. And like before, we can also look at the actual per pixel optima, the optimal per pixel phase shifts. And in this case, that's the same data set as the one before, the one with the very strong aberration. And here we see that the true CTF is running ahead of the expected one in 4 directions and lagging behind it in 4 other directions. And this can be expressed by our Jasenko model again. And when you look at the corresponding CTFs, so here you see the original one and the distorted one. So note it becomes slightly angled up here. But there's very little change around the origin. So you could never measure this by just looking at ton rings. Those are way too weak. You need to accumulate the data for an entire data set to estimate those. So this actually does make a difference in some cases when it really is a problem. We found this is the most extreme data set I've found, this proteasome, where we start with 3.3 angstrom, and then by correcting both the symmetrical and the antisymmetrical aberrations, we can get all the way to 2.5. Right. Okay, now the anisotropic magnification. This is related. Yeah, I assume you're familiar with it. Microscopes sometimes magnify to different degrees in different directions. So the image that we observe is contracted or dilated compared to the true one. However, the reference map that you obtain, the particles of the sample, we can, I think, always assume that the in-plane rotation angle is completely arbitrary. So that the 3D projections of the 3D reference map will never show any anisotropic magnification, or no significant one. So we can compare the predictions with the observed images, and in this case, the approach is to try to find shifts, that is translations for every pixel. Again, every pixel in Fourier space. You can express the stretching and squishing of an image in Fourier space or in real space. It's the same, the matrix is just inverted. And ultimately, we then expect these shifts to line up along a linear manifold, if this is really a stretching or squishing that we're observing. And formally, what we do is now we can have this reference. Now again, without the CTF, it's on the outside. And we want to find small displacement vectors delta k, at k, for each k, so that we can minimize this square loss. And now, to make this nicely linear again, we perform a Taylor expansion. This is an approximation, of course, now. And so we assume that the value, the complex amplitude of the predicted image at k plus delta k is equal to v at k plus the gradient of v at k dot the displacement delta k. And when we do that and plug it back in here, it's all nicely linear again, like in the previous case. So we again just need to iterate through the data set once, accumulate a symmetrical 2x2 matrix that's just 3 distinct numbers and a 2 vector. So it's 5 vectors, 5 numbers per pixel altogether that we need to track as we go through the data set. And when we're done, we can determine these displacements at first. And when we look at them, you can probably see it better over there. So you do see that they do, so here you see the 2 components of the per pixel displacement. And you see how they do line up along linear manifolds. And if you interpret that together with the coordinates, it means that the x direction is, the x coordinate is squished and the y direction is stretched, and at a slight angle. Right, and now these displacements are not useful, of course. They just tell us that there is magnification. We can, instead of estimating these per pixel displacements, we can just estimate one magnification matrix M. So we want to find a matrix that, when applied to the coordinates in Fourier space, gives us new coordinates that are similar to k delocalized by delta k. Right? And this is again nicely linear. And we don't need to do anything new. We just we have all the terms that we need from assuming we've computed the delta case. So we can solve this in fractions of a millisecond probably, because it's nicely linear. It's just it's just 4 unknowns that we are looking for. And that's it then. And we have this M. We can Reliant is now aware of it, and then there's never any need to resample images as people used to do. Reliant just needs to know where to insert a pixel in the 3D volume. Also, another caveat: the M is, I have defined it as general as possible. It's really a general 2x2 matrix, so it's not necessarily symmetrical. So it cannot necessarily be expressed as just 2 magnifications and an angle in between. But it can also have a skew component. This is known for light cameras. We have seen no evidence that it actually happens in Cryo-EM, but Reliant would support it. And if you would like a symmetrical matrix, you can symmetrize it. And the results of this are consistent with more traditional methods. However, this can be done after collection, so you don't need access to the microscope to do it. It only helps, however, if there is significant anisotropy, and that is rare. What it also does, however, is it allows us to estimate the relative magnifications in a heterogeneous data set. So sometimes people merge images collected on different microscopes or the same microscope after alignment. So the magnification is maybe nominally the same, but in reality it varies by a couple of %. And with this method, you can now estimate the relative magnifications of the different sub-data sets. And finally, it's the last thing that one can do. It usually produces a small improvement, but because there usually is some little bit of anisotropy. So with this together, we can now approach what we shouldn't report as 1.5, but we can approach the highest resolutions that we've measured so far. Well, reach. Right, also on a more practical side, so now it's maybe not too interesting to this audience actually, but we support a new concept of optics groups now. So all the optics-related quantities only need to be constant within one such optics group. But we can now refine data coming from different microscopes with different voltages even. And all of them can be refined together. And we can use the anisotropic magnification estimation to estimate the relative magnifications of the sub-optics groups. And the second thing, there is now also a new per micrograph global estimation procedure for the remaining low-order CTF terms that I haven't talked about very much. So with this, you can now estimate the phase shift, the defocus, the astigmatism, the spherical aberration, and the per particle B and scale factors, each of them either per micrograph or per particle or not at all, that is leaving them fixed. Right, thank you very much for your attention. And please ask your questions now.